All right, welcome to CAM 395, Experiment 4, X-ray diffraction and fluorescence. And in this video, we will learn how to calculate the theoretical intensities for the salt samples. So this exercise is going to be an extra credit. And thus, I will assume that if you are watching this video, you have watched the other two where we did the indexing exercise and calculate the theoretical intensities for the metal samples. So again, equations taken from the handout for convenience. And also there are several crystal structures here corresponding to the salts that we have. Again, just for convenience, taken from the course website. Right. So now, if you're at this point, I would assume that from the metal sample calculations, you know how to set up all the calculations from 2 theta, converting the units, getting the HKL indices and their multiplicity, and then obtaining the temperature independent scattering factor, or F0. Now, the difference here is that for a salt sample, or binary salt to be more precise, we need to take into account the scattering factor for both the cation and anion. In this calculation, I will assume that my sample is sodium chloride, which has an FCC structure, for example. So here, based on the reference, I have obtained the value for my temperature-independent scattering factor, and then I use the Debye-Waller factor to incorporate temperature dependence. And now the question is, how do we proceed from here? Because you might be tempted to just add, the scattering factor together, and then use that as the total scattering factor, and then proceed with the intensity calculation as in the metal sample. Well, it will boil down to something similar, but I can assure you that that is not correct. So we need to actually take some extra steps to ensure that we have the correct scattering factor for salt calculation. So here we see that for salt, the intensity, now the scattering factor is described by this capital F, where this capital F is the sum of this little f, which is the scattering factors we've used before, multiplying this term in exponent, where this describes the phase difference because of the different positioning of the ions inside your crystal structure. So now, if we take a closer look at what is inside the exponent, we see that it's 2 pi multiplying the HKL index and the XYZ coordinate of the ions sitting in your unit cell, being a dot product of them. So H times X, K times Y, L times Z. Now, the tricky thing about this is that now we have to know the coordinate of all ions in our unit cell. So now we have to figure out how to do that, and that's why you have to know the structures a priori, and that's why this is an extra credit exercise. So let's try and do that and try to obtain the phase factor here so that we can calculate the total scattering factor. Okay. So, all right. So let's focus here. Let me zoom in. Okay, so let's focus here on the structure of NaCl, which I figured out by doing the indexing and making sure everything's proper. So it's an FCC. Here, the black atoms or ions here are the Cl minus, and the white ones are sodium pluses. And actually, you can also reverse the ordering, and you will still get the same crystal structure for NaCl. So here, let's imagine that this is my my x-axis. This is my y-axis going inside, and z-axis is vertical. And let's imagine that we try to look at the unit cell from the direction of the z-axis. So from this top, this is the smiley looking down to the unit cell. And now let's figure out the coordinate for the ions slice by slice, right? Plane by plane. So let's start by looking at the z equals 0 plane. So we have here x and y coordinate, which is corresponding to this bottom square here. So again, we can imagine that now we have Cl minuses in the corners, as well as in the center of the face. And then we have sodium pluses on the center of the edges, right? So that's how my z equals 0 plane looks like. So for example, if I want to get the coordinate of this Cl atom, we know that it's going to be 0, 0, 0, because it's the origin. So it's this one. And now we use the convention where when we get to the other edge of the unit cell, it's 1 unit. So for example, the coordinate of this chloride ion will be 0, 1, 0, because x, y, z. And the center of the face will be 0.5, 0.5, 0. Now for the sodiums, we can also do the same thing. For example, center of the edges, this one will be 0.5, 0, 0. This one will be 1, 0.5, 0, and so on and so forth. And then we can go to the next slice of our unit cell, where now we have sodium in the center and on the corners of the square, and then chloride on the edges. And we can do the same exercise, obtain the coordinate. And then we do the same thing for the top layer, and which is going to be similar to the bottom layer, except now your z is going to be 1. Okay, so now once we have the coordinate of the ions, now it would not be a bad idea to compile a table that looks like this. So here I have my HKL indices for each of the angle, right? So 1, 1, 1 for 3, 2, 0, 0 for 4, and so on and so forth. And here I'm doing x, y, z from top to bottom. So for example, here, these are the center of the edges. So here, I have the z equals 0. That means I'm looking at this one. And I have my sodium, which is going to be this one, 0.500. And I will have this one, 1.50. And then I'm just going counterclockwise, 0.510, and then x0, 0.5, z0, right? And you compile it for all of the ions that you have, and you want to make the table separate, one for sodium and one for chlorine, or one for sodium plus and one for chloride, to be more precise. And in your case, it's going to be one for your cation, one for your anion. And you also want to separate the tables based on their location. So here I am grouping sodium that are on the edges together. So there should be 12 of this thing. Here I group the sodium that's on the center of the cube by itself, because it's only one. Same thing for the chloride. Now my chloride will be in the corners of the cube, so there will be 8 of them. And I also group them because there are some that will be on the center of the faces, so there will be 6 of them. All right, so the reason why we are doing this grouping will be clear once we do the calculation. Okay, so now once we have this table, what do we need them for? So remember, our original intention was to calculate the space factor, which is 2 pi times hx plus ky plus lz, and then plug them into the exponent. Now, the cool thing is that you know that you can expand using Taylor series, or e to the number multiplying I can be regarded as cosine. Say if I have e to the ix, I can write it as cosine x plus I multiplying I sine x, where I is the imaginary number. And if I have cosine of minus ix, I can put it, or if I have e to the minus ix, I can have it as cosine x minus I sine x, right? Now, because this is a trigonometric function, so if the argument here is pi or 2 pi, so we get some special numbers that says 1. If the number multiplying pi I is an even number, or minus 1 if we have an odd number multiplying pi I in the exponent. So that's exactly what we will look for here. Are we getting an even or an odd number? In some cases, depending on your structure, you will also have something that will be 1.5 times pi I, or that kind of fraction. And if you try to convert it using this formula, you will actually get a complex number. So in that case, I would just take the real part of the complex number, which is actually going to be 0, and just to keep it simple, right? So don't worry if you don't get an odd or an even number, or not an integer, basically. Just put it as 0, all right? Okay, so let's do this, which is going to be fun. So now we want to multiply h times x plus k times y plus L times Z. Okay. So now here we know we want to replicate it across and down. So we will block the appropriate places and go for the best. If we set this up properly, we will be able to just do this without much complication. Right? Now, because we want to know whether it's going to be an even or odd number multiplying pi, so we should also multiply this whole thing by 2. So we know it's going to be this number that we have in the table multiplying pi I, right? Okay. All right, so we have that, and let's have it across. Oop. All right. And let's not have the border. Oh, that was a mistake. Okay, let's have it this way. Okay. And then we do the same thing here. And now here we need to do again this x plus a times y plus L times everything multiplied by 2. And here, again, we need to lock the appropriate places. Right? Okay, so now we have all the numbers that we need actually. So here, we see that it's going to be sum for each of these coordinates. So for each of these coordinates, it's going to be 1, -1, or 0. But now we have to take care of how many cubes share the ions that we are interested in. For example, if we're looking at the edges, the sodium ion here is shared by 4 cubes, which means once we have figured out how many of this are +1 or -1, we have to divide it by 4. It applies to the corners, divided by 8, and center of faces, divided by 2. This is in the center of a cube, so we don't need to divide it by anything. Okay. So here we see that all of this HKL multiplied by 2 is giving us an odd number, right? And we recall that if it's an odd number in the exponent, it's going to give us -1. So each of this is going to be -1, -1, -1, all the way. And we have 12 of them. So it's going to be -12 divided by 4. So it's going to be minus. Here, it's all even. So it's going to be +1 for everything. So it's going to be +3 because we have, or 3, because we have 12 divided by 4. Here again, it's all even. So it's going to be 3. Here it's all odd. So it's going to be -3. Here it's all even. So we will have, here we do the same thing, because now we have 1 and we don't need to divide by anything. So it's going to be -1, 1, 1, -1, and 1. Okay. So now the total phase contribution for the sodium plus for each of this plane is just the sum of these two numbers. Okay. So it's going to be -3 and -1. You sum them together. All right. Now here for the chloride, they remember when we tried to do this assignment, I said that my Cl minus is going to be in the basic FCC. So it's going to be in the corners and the face centers. And as you can already see, everything gives us an even number for the exponent. So all of this will be plus, and then we just have to take care of how many atoms there are. So this one have 8 times 1 divided by 8. So everything here is going to be 1. Here we have 6 of them, but we have to divide by 2. So it's going to be 3. 3 of them. So as you can already expect, the total contribution here is going to be added together. All right. So this is the hard part. And the cool thing about this table is that if you try to do this table for only for your metal sample, for example, you will find that it will have this kind of characteristic where all of the numbers will be positive for all the picks that you have. However, let's say you have an FCC lattice, and we know that in FCC, your HKL indices have to be all odds or all even numbers. Now, if you try to, for example, do a calculation with HKL equals 100, which is not part of the FCC Miller indices, you will find that it will not contribute to the diffraction, and the sum here will be 0. And because this is 0, you can see that when we try to calculate the capital F, it's going to be 0. So you will not see peaks coming from that particular plane. All right, so now, once we have this number, if we go back here, so now we need to take into account all of this total phases, okay? So for sodium, as you can see, there are some minuses, and I will just paste the value. Here, everything is positive for chloride. So let's again paste just the values. All right, so now we will see something very interesting coming up from this calculation. So now if I do the capital F for sodium plus, it's just going to be in the phase factor multiplying the scattering factor that we already got from the table and from the Debye-Wohlert coefficient. Now, for the chloride, we will have the same thing. Okay. So for the F total, now it's just the sum for the cation and the anion. Now, here from the F total, you can already see the consequence of this phase factors. Now we can see that your first peak for a salt is not necessarily going to be in the largest or the tallest peak anymore, because you might have a destructive interference coming from the sodium planes and the chloride planes. For example, here my second peak is actually the tallest one. Right? And again, that's exactly what's causing some of the peaks to not appear in the in your Miller indices, in your peak progression, right? So now once you have this F total, the rest of the calculation is going to be the same, where your intensity is just the multiplicity times the F total squared times the numerator divided by the denominator, and you can continue doing the calculation as usual. Normalize. And exactly, as you can see, it's already pretty close to what we see in the experiment, where my second peak is the tallest one, and then the rest is smaller. Okay, then of course we can do the absolute difference, and then try to optimize to obtain the R value as usual. Right? For the sake of completeness, let's do it up until this point. And at this point now you're set to do the solver. For example, we can do the quick scan to see how things are going to look like. All right, so it looks like if I have it at around 2, between 2 and 3, maybe it's going to give me the optimum value. And then you can play with solver, get your optimum B value. So that's it, and have fun with calculating the theoretical intensities for your salt samples.